Angshuk Dutta. So our agenda for today is I will take you through the objective of our problem and the introduction to our problem, and then Angshuk will discuss the methodology and the experiments with you. Finally, I'll conclude with the results and then the implications of our project. So the objective of our project is to pose an alternative solution relying on surveillance images and CCTV footage to identify the close contacts of COVID-19 patients by leveraging deep learning techniques. So what is the need for this solution? In order to take a look at that, we'll go to the introduction. So we're all familiar with COVID-19. It is an infectious disease that has been transmitted globally at this point since the past year. So the transmission of this disease is through saliva droplets and discharge from the nose of an infected person. And the best way to prevent transmission is to maintain social distancing of at least 1 meter between two people. Moreover, wearing masks decreases the transmission rates too. So it is obviously very important to contain any spreaders of this disease and to isolate anyone at risk of contracting the disease. The way we do this is through contact tracing. So there's manual contact tracing where the patient and recounts through memory whoever they've been in contact with, but this is not very reliable. So the new method is digital contact tracing, which relies on Bluetooth signaling actually. So it uses smartphones as a proxy for people and estimates distances between smartphones as distance between two people. And it uses this to identify who the close contacts of a COVID-19 patient are. But of course, this is not very reliable either because all of these apps are on an opt in basis. Moreover, enforcing this kind of app based contact tracing is very difficult for governments and is not usually very successful. So, to combat these problems, we have come up with a solution based on surveillance imaging. So, we use CCTV footage in order to conduct contact tracing and to estimate the distance between two people and to thus identify close contacts of a COVID-19 case. We can also identify who is wearing a mask or not for an added bonus. So let's discuss the formulation of our problem. Now let's consider this case. There is a person, PI, in an enclosed or confined space. The probability of them wearing a mask is 0. Now a new person comes in, PJ, as you can see in this image. So the probability of them wearing a mask is 1, as you can see that they are wearing a mask. So the distance between these two people is Dij. So the problem we have at hand is to calculate the probability of person J contracting the virus from person I, if they do turn out to be positive. So now let's move on to our methodology. I'll hand over the rest of my time to Angshuk.
Hi, everyone. So I'm going to be speaking about the methodology. So the problem which Spriha mentioned, I will now break that down into smaller subproblems, and I will in the form of steps. So our first step is mask detection, where we aim to infer whether a person is wearing a mask or not from the frame that we obtain from the CCTV footage. The second step is person re-identification, where we infer whether the same person appears in different frames from a CCTV footage. The third step is distance calculation, where we calculate the distance between two or more people. And this is also a very important step because this is where social distancing comes into play. And our last step is probability calculation, where we introduce our own empirical formula to calculate the likelihood that a person will contract COVID from other infected people. Okay, moving on. Our first step is mask detection. So over here, we have employed the model VGG19 with batch normalization. The VGG19 model consists of 19 convolutional layers, and the input it receives is the frame from the CCTV footage. So let's take our example here. Here we have a frame with two people, the first person wearing a mask and the second person not wearing a mask. The output of this model is basically two probabilities. The first probability indicating that the person is not wearing a mask, which is indicated here, this is 0. And the second probability that the person is wearing a mask, that is indicated by this here, that is 1. And the overall random variable is empty. We employ batch normalization here because it increases the accuracy of our model. Moving on to the next step, we have person re-identification. This is actually one of the most important and one of the most difficult steps to implement because of the following reasons. The first one is being low resolution of the CCTV cameras. The second one being occlusion or objects blocking the face of a person in the frame. The third one being different angles the cameras are positioned at, and so on. This makes person re-identification an open problem in research. Current state-of-the-art methods use CNN-based architectures to solve these problems. However, we have employed a transformer model for ours. The reason being that CNN has a narrow receptive field. What do I mean by receptive field? It means that every layer of a CNN receives a smaller and smaller input, that it receives the salient features or the most important features that are extracted by the layer. However, the transformer model has a global receptive field where it learns the association between the different pixels in the entire image. And for person re-identification, this is very important because different parts of a person may be blocked by different objects or may even be blurred by the low resolution of the cameras implemented. So let's take the example of our system here. So let's see how it works. So we have a set of images here, which are passed through the transformer model, and then it's passed through the self-attention layer in the transformer model to give a set of embeddings. These are indicated by the vector here, and Fi and Fn indicate the ith and nth embedding. Next, we pass it on to this very interesting module. It's called the jigsaw patch module and is implemented by the works of Hay et al. And what it basically does is that it basically breaks this global embedding that we have here into smaller sub-embeddings. That is, each embedding at Fi and Fn are broken into k such sub-embeddings. And this k is determined by the hyperparameter and is decided by us. So these embeddings, these sub-embeddings are then passed through a transformer layer again, and we learn the different associations between the different broken embeddings among each other and also among the global embeddings themselves. And we get this patch embedding here, which is indicated by the different patches and the braces. Now, what we do in the next step is we shuffle these patches so that we do not learn correlations between the patches themselves, but correlations between the different pixels in the patches themselves. The next step is we concatenate these embeddings along with our global embeddings Fi and Fn to form a new representation. This representation is then passed through a classification block, and then we get a new embedding Gi and Gn, which is robust and invariant to different things, like the low resolution or even occlusions where an object is blocking a person's face. Moving on to the next step, we have distance calculation. So let's take our example here where we have an image with two faces and each of these faces surrounded by a bounding box. This is given by our mass detection model. So the first step that we do is calculate the Euclidean distance between these two faces, and we get a distance. However, the distance that is calculated over here is not standardized across different frames. This is because the bounding boxes may have different widths or different shapes depending on the frame and the depth of the face from the CCTV camera. In order to standardize this or get a real life ratio comparison, we calculate from our research, we observe that the average face width of a person is actually 18 centimeters. So that is why we standardize we calculate a scaling factor and standardize it based on this value. So if we see here, 18 is our average face width, and in the bottom, we have the average of the bounding box side lengths. Once the scaling factor has been calculated, we then multiply the scaling factor to our Euclidean distance to get a real life distance. Moving on to the next step, we have probability calculation. So in this step, we introduce an empirical formula that is based on our experiments, but this probability calculation really depends on the needs of the region and the current research that is being done in the healthcare industry. So in our case, we emphasize social distancing. So we have a general probability formula here, which is denoted by 100 minus d by 100 when d is less than 100 and 0 when d is greater than 100. Note that d over here is actually the distance between the two people, pi and pj. So why is it 0 when d is greater than 100? So in our case, the 100 is 100 centimeters on 1 meter, which is the social distancing norm. So we say that it is 0 when it is absolutely greater than 1 meter. And the 100 minus d indicates that the smaller the distance between the two people, the higher the chances of getting COVID or contracting COVID. So now we have our final probability function, which takes into account whether a person is wearing a mask or not. And depending on whether the person is wearing a mask or not, the probability can be decreased by 20% or more. Okay, moving on to our experiments. So the first step that we have is the data sets. So we have two folders here for mask detection, which is the masked images and the unmasked images. For our masked images, we have 27,024 images, and for our unmasked images, we have 41,084 images. Moving on to our person re-identification data set, we have equal number of images for both masked and unmasked, which is 6,595. Moving on to the metrics that we use to evaluate our model. So for the mask detection model, we use the test accuracy to evaluate our model. And for a person re-identification model, we use the mean average precision. So let me explain what mean average precision is. And for that, I need to explain what average precision is. So let's say we have an image from a frame and that we are trying to compare this image with the other images that we have in our database and get the unique ID for that person. So what we do is see after comparing it to all images in our database, we get a ranking based on a similarity score of how similar our query image is to all the other images in the database. If our image is say, if the right image pops up in the first value, then we say the k value over here that you see at p at k and rel at k is 1. That means we got the right image or the right ID at the first try itself. However, if we don't get in the first try, but in the top two, top three, and in the top n, the k will take the values of 2, 3, and n respectively. So the average precision is just the sum of these and averaged over the number of queries that we have. The mean average precision then is just the average of all the average precisions based on the number of queries. So now moving on to the results, I will pass on the mantle to Spriha.
Okay, thank you, Angshuk. So let's look at the results for our mask detection model first. So we chose the VGG19 model with batch normalization, and the reason we did that is apparent from this slide. So this model uses relatively fewer parameters than the other models, while also maintaining an impressive test accuracy of 100%. So as you can see, our mask detection model works quite well since it is so accurate. Now let's look at the person re-ID results. So for this one, we implemented the VIT16 model with Jigsaw Patch module. So as you can see, when we compare the results with the baseline model, we get much better results with the Jigsaw Patch module, which is why we went ahead with it. If you would like to take a look at our comparison with the CNN-based models, you can take a look at our paper. But of course, these are very abstract results. It will be better if we show you an actual demonstration. So as you can see, we have our friend Angshuk's face here on the slide, and the model can detect whether he is wearing a mask or not wearing a mask successfully. And we also have a demonstration of our person re-ID and the probability calculated. So actually, we took a number of different cases where there is a person 1, 2, and 3, and they are either wearing a mask or not wearing a mask. So as you can see, the likelihoods of everyone contracting the virus from another person are different because it depends on the distance between them as well as if they are wearing a mask or not. So in this case, since person 1 has a likelihood of contracting the virus of over 50%, they will probably be quarantined first and be treated as a high risk contact. So this is quite useful in order to isolate people progressively. So now to move on to the conclusion of our project and our implications. So as we have seen, it is the need of the hour to have a robust contact tracing system that takes into account both social distancing as well as whether a person is wearing a mask or not. So we calculate the probability of an individual contracting the virus based on these two factors. Of course, we came up with this empirical formula, but it can be tweaked depending on the region and on what is important in that particular region. So this project has the implication of being deployed by governments on a large scale and also by private organizations in workplaces and in offices. So it is quite useful as long as there is surveillance data available. So our project uses different models like VGG with batch normalization and transfer ID to implement these separate processes smoothly and to integrate them into one combined system for COVID-19 contact tracing. And as you have seen, our results speak for themselves. So thank you so much. And I hope that all of you take care of the mask rules and maintain social distancing. Thank you.
Thank you very much to our presenters, Spriha and Angshuk. The floor is now open to questions from the audience. So if you have any questions for our presenters, please type them into the Zoom chat or on Huba, and the presenters will address them. So we have a question that says, how well can this system perform in crowded areas?
Okay, thanks for the question, Peter. So in terms of crowded areas, so our mass detection model and our face re-ID model are actually perform very well in crowded areas. The only hit I think I would say that this model would take is actually in our time that it takes to calculate the result. So obviously right now, due to the lack of resources, we are just running it on our local GPUs. But of course, with better resources and definitely a more centralized server or something like that, we can definitely increase the time that it takes to run. I mean, definitely decrease the time that it takes to run. So yeah, I hope that answers your question.
Thank you for your question, Mac.
We have a question from Matt.
Oh,
Yeah.
sorry.
It says,
Yeah.
how do you think your project can be made scalable and usable across countries? In times such as these, when privacy concerns are growing day by day, what is a possible solution to this problem without compromising on the surveillance itself?
Okay. Yeah. So obviously, privacy concerns are a matter of importance. However, that just depends on the permissions that the organization has or the government. So, for example, if the government is deploying the product at such a scale, at a large scale, then it is up to the government to use the information that is publicly available. And of course, there are privacy concerns, but I would say that the privacy concerns are more so with the smartphone based data and the current Bluetooth solutions, because those are third party apps in most cases, and that is more compromising. And in case of a large organization that is implementing our project, in that case also, the CCTV footage will be of that organization itself in its own workplaces and offices. So they will have the required permissions to carry out this project. I hope that helps.
We have another question. Do you think your solutions would be more efficient and cost effective than current solutions used by governments like Singapore and South Korea, where they use Bluetooth location services as well as ID or credit card details to alert citizens if they have been in close contact with COVID positive individuals?
Thank you for your question. So, currently, there are solutions being put into place by countries such as Singapore and South Korea. However, they use a number of different data, such as Bluetooth location services and these details, as you have mentioned. So, I think that our solution is more cost effective because we are using our deep learning techniques. And moreover, we are focusing on surveillance footage, which will be available depending on the scale of deployment. Now, it is obviously important to make sure that this is the case. So that will be conducted in further testing, and that is the future of this work, in fact. Would Anshuk like to add anything?
Yeah. So basically, the thing that I wanted to add is I just wanted to add on to this point that is in the question, the ID or credit card details. So our work also takes in all this information in the database itself. So the government already possesses information like passport photos or some for people. So that itself can be used as a comparison for the person re-ID part of our model. And secondly, we all know that even the current services like Bluetooth and stuff, the government also uses the people also use their own databases to get the person's ID for contact tracing, or the systems, or the healthcare systems also do that for contact tracing to get the people's names. So I think in terms of like, I think basically we're making it a slightly easier to deploy such solutions because in Singapore, it's very well deployed. We have safe entry. However, in other countries, this may not be the case. But we know that CCTV cameras are employed in most big organizations, malls, and so on. so we can ensure safe contact tracing everywhere. Yeah, I think that's all I wanted to add.
Okay, thank you. If any audience members have any questions for the presenters, please type them into the Zoom chat. I can ask a question. Do you see any other possible applications of this technology outside of contact tracing?
Okay. I think for sure. I think like the maybe if we could change our project a little bit, I think the person DID and maybe like face identification is already has already big applications in security and used by a lot of is enforced in a lot of security protocols and stuff like that. So I think we can already see the implications of these two technologies themselves in other sectors. But I think the distance calculation and definitely the probability calculation are very specific to our project. So I won't say that those can be deployed anywhere else, but the person ID and stuff are very generic technologies, and I think has a lot of implications, and one of them being security, of course. Hope that answers your question.
Yep, thank you. I do have one quite specific question regarding the K hyperparameter you mentioned.
Yeah, sure.
How did you decide what the value of that is?
Of the hyperparameter. Okay,
Yeah.
so the basically we did a grid search sort of way for the hyperparameter. So basically we took a small range of values. So the hyperparameter is actually a probability value. So it ranges from 0 to 1. So we can basically just take a small gap, say from 0.2 to 0.5, and that much of the data is shuffled, or that much of the thing is randomly shuffled. The random shuffle function basically just randomly shuffles it anyway. We don't have control over that, but we do have control of how much data is being shuffled. So we just ran a grid search way, and we basically saw which one gave us the best results. Yeah, that was it for the training procedure. Yeah. Hope that answers your question.
Yep, it does. Thank you. We'll wait another 2 minutes to see if anyone from the audience has any questions. If not, we will move.
Hi, we'll just wait for another 2 minutes if we have any more questions from the audience. If not, we can move on to the next one. So just give it 2 minutes. Thank you.
I think we have an audience question.
Yeah, we have a question that says, what were the major challenges or roadblocks that you faced while programming your solution?
Okay, so the major challenges that we definitely faced was actually training our person re-ID model. And that's probably because of the amount of GPU memory it actually takes. So definitely incorporating that and making it fast. So right now for around 6 to 7 faces, it takes about 20 seconds. So yeah, but that was actually one of the major challenges, I think, was just to make it swift and adaptable to scale, basically. Yeah. So that definitely requires more work, and I think with maybe more resources, is definitely can become much much faster. But right now, to the best of our capabilities, this was our major challenge. I hope that answers your question.
Okay, great, thank you. Our time is coming to a close, so I would like to thank our presenters for your answers and your presentation. And I would also like to thank the audience for attending and participating. Our next event is another student presentation happening in a few minutes. So to attend that, please head to Huva to find the appropriate Zoom room. Thank you all for listening, and goodbye.